working with logarithms. As many of you probably figured out, because that's what the next section is in the book, the base rule that you need to make sure you understand and can do. This is the same as a to the c equals b. So these two statements are in all ways equivalent. So let's write a statement here. So give me a base. 3. Okay, give me an exponent. 5. What's 3 to the 5th? 243. Okay, so now we're going to rewrite it in logarithmic form. What is my base here? 3. So I'm going to write log base 3. This is our base of 243 equals 5. So this is an important thing. You need to be able to change back and forth between these two forms at will. Any questions on how that works? Have you seen these before? Okay, good. So it's not new. So what would, say, log base 2 of 64 equal? No calculator. Calculator. It is 6. The question you can ask yourself is 2 raised to what power is 64? So 2, 4, 8, 16, 32, 64, 6 power. Or say log base 4 of, let's say, 1 over 256. 2 raised to what power is 64? Okay, so we're saying 4 to what power is 256? And that's 4. However, because it's 1 over 256, we get a negative number. Okay, you with me? So, I believe there are some. Now, you know how to do this on your calculator. Because you look at your calculator, you've got a log button right here. Then we do right here, log. And we've got another log button right there. We'll talk about those two log buttons. Yes. So those are your logs. Some of your calculators are able to you're able to change the base. Yeah. If you have an 84, I believe you can go into your you can find our math. The 83 does, I don't believe has it. Let me see.
Yep. Nope.
Yeah. So the 83 does not do it, 84 does. 89 does, if you know how to do it. Okay. So we want to talk about some properties of logarithms. Log base a of 1. Log base a of 1, what is it equal to? So a raised to 1 is 1. So the question is, a raised to what power is 1? Are you sure? Okay. So 5 raised to what power is 1? 15 raised to what power is 1? Pi raised to what power is 1? 0. Okay, so one of our rules is if we have a base, log base company of 1, we get 0. How about this one? Log base A of A. 1. Because A raised to what power is A? 5 raised to what power is 5? 10 raised to what power is 10? Yes. Now a bit more complicated. Log base A of A raised to the x. A raised to what power is A to the x? X. So think about it. If I did log base 2 of 5 to the third, or no, sorry, log base 2 of 2 to the third, 2 raised to what power is 2 to the third? It's just 3. Because remember, when we have this form, let's just put m here. Let's change it back to exponential form. We would have 2 to the m equals 2 to the third. What does m have to be? 3. So you can say m equals 3. So if you're confused on what to do, sometimes it's helpful to change it from the logarithmic form to the exponential form, and then you might be able to see a way through it. And let's see, next one on my list. Even more complicated. A raised to the log base A of x. And then have a guess what it's going to be. Okay? It's actually that logarithms and exponentials are inverse operations. So one of them will undo the other. So when you look at this one, we had a logarithm applied to an exponent. They cancel. Just as like if we had the cube root of 4 cubed. What's this going to equal? 4, because the cube root and the cube cancel. They are opposite operations. The cube root and cube. When we look at this one, the log base A and A to the x, they are opposite operations. They cancel, leaving you with x. And the same thing applies here. If I took this one, so I said the cube root of 4 to the third. What if I did the cube root of 4 raised to the third? Do they cancel out still? Yes. And the same thing here. A raised to the log base A cancel, leaving you with just x. Okay? It's basically they're designed as opposite operations. We'll look at a little bit. We'll be looking at the graph in a little bit to say, so these are actually inverse operations. Like addition and subtraction are inverses. They cancel each other out. Multiplication, division, opposite operations. Logarithms and exponentials, same deal, opposite operations. However, there is one restriction I'm going to put on this. X has to be greater than 0. Now, why do I have to say that? Let's do a little problem here. Log base 3 of negative, let's say negative 9. 3 raised to what power is negative 9? We've got a problem here, right? Because we could do 2 to get positive 9. Negative 2 gives us 1/9. Can you raise something to a power and get a negative number? Not if it's a positive number. So negative numbers are not in their domain. So let's look at what the graph of these. graphing. So on your calculator, for now we're just going to use your base log. So log x. Anybody have a guess what it's going to look like before you actually do it? For now, just do the ln. Okay. So, what do you see about this graph? Okay. So it looks like it doesn't have an asymptote. Okay. It looks like it has a vertical asymptote, right? Can I plug in negative numbers into this? Let's see. If I plug in -3, doesn't work. How about, what about 0? Will 0 work? No, clearly not, because I put in 0 and I get nothing. How about 0.01? So, what can we say about the domain and range of this? So just do y equals log x. What's the domain? Okay, positive. So we're going to do 0 to infinity. Note, not bracketed 0. What's the range? Okay, how low does it go? Negative infinity says? You agree? Okay, so I could put in, say 0.000, bunch of zeros there and something, and get negative 9.6. However, if I make a small enough number, eventually I'm going to get down to negative. So, negative infinity, how high does it go? Infinity again. Okay? Asymptote. Y equals 0. Or x equals 0. Which one?
Y. X equals 0.
Okay. So when we talk about logarithms, that's what we have. Now, what if we had y equals 10 to the x? What is the domain of this one? Do you remember? Okay, all real, so negative infinity to infinity. What's the range? Or that's what we talked about on Monday. What's the range of this? All positive numbers. So 0 to infinity. Asymptote? What is it? Y equals 0. Do you see sort of a pattern between these? Let's highlight some things. Domain. So just look at these three features. Do you think there might be some connection between the graphs? Yeah, they are inverses. So when we talk about inverses, remember we talked about that earlier this year, we saw some sort of pattern like this. And if we follow this exact, we would get this exact pattern where the domain of one is the range of the other. Now, what about graphing one of these manually? So, graphing a logarithm. Y equals log base 2 of x. Because I'll say very likely on the test, they'll be on the no graphing or no calculator part, perhaps of this. Or they'll even make it more fun. Plus 3. So what is that plus 3 going to do to it? Plus 3 units. And if I put a minus 1, what would it do? Down 1. So everybody seen this pattern, right, that we've just been doing like this at the beginning of the year? Okay. So what would be a convenient number to plug into this? Okay. If I plug in 1 is a better number than 0 in this case. Why? Yeah. If I plug in 1 for x, 2 raised to what power is 4? 2. So at 1, we are at 2. So x, y. If we choose 1, we have 1 plus 3 is 4. And 2 raised to what power is 4? 2. What would be another convenient number to plug in? 2 plus 3? 5. 5 is probably a good number. 5 plus 3 is 8. 2 raised to what power is 8? So at 5, we should be at 3. What's the more nice number? Lower nice number. 13 would work, but our graph is less 13. Okay, negative 1. Negative 1 plus 3 is? 2 raised to what power is 2? 1. So negative 1 we're at 2. Or 1, sorry. Okay, negative 2. Negative 2 plus 3 is? 1. 2 raised to what power is 1? 0. Now what's going to happen after here? Remember we had plug in fractions. Remember we get an asymptote here. If we had an asymptote at 0, we've moved it over about 3 spaces, therefore it's at negative 3. And so now you can draw the graph in here. Do you follow that? How we did that? And you see how we can choose good numbers to plug in. Okay? Our goal with these, when we're choosing those numbers, is what numbers do we plug in here to get powers of 2? The powers of 2 were 0, or 1, 2, 4, 8, 16. Those are how we choose these numbers to plug in. Makes the graph much easier if you chose that. Because notice we could plug in any number we wanted. However, then you couldn't do it by hand as easily. It would be much more challenging, and it's much easier to do it on the calculator. But this one, if you choose the right numbers, it's easy to do by hand. Now, a couple more basic things that we need to know. Well, no laugh. That's fine. Okay, a common log. This is the button your calculator has, it's the log button. So if you see just log by itself, so if I say log x is the same as log base 10 of x. So the log button on your calculator is the same as just saying log base 10. And it's known as a common log. Now, as a precaution, there are some places and some books that use the next thing as your common log. However, this is what I've seen in almost everything I've used. However, if you read some English textbooks and stuff, they'll use the natural log as your common log. The natural log is the next one we're putting up here. This is equivalent, or is defined as, is probably a best term. When you see that, we're defining this as this term, rather than just saying these are equal in this case. These are defined, a definition. So, you have this button Ln. This is known as the natural log. which is the same as, in all ways equivalent, so it's defined as at log base e. Now, what I'm saying is some people or some places use this, when you see just this, as the same as ln x. However, you won't see that very often, and if you do, you can just frown and ignore it.
Is it wrong?
Not really. It's just different. Like we here in the United States, we usually say math, right? In England, they say math. Why is that? Does it make sense to say mathematics? We say mathematics, plural, and so generally when you shorten the word, you keep the plural.
I don't like it.
Yeah.
Calculator shifter, what we call it, the tricks on the calculator for changing
Yes.
the base.
I'm going to show you that. So, since most of you have CID3 or something like that, to do what's known as a change of base formula. So, change of base. Now, you shouldn't really need this because most of these you should be able to do by hand. So in case you're in doubt, there will be questions like this on the test where you have to do it by hand. Pi raised to 1 power is 125. 3. So, if you're doing it on the calculator, you may use either the natural log button, which is what you have common, or the common log button. To simplify this, we can just do ln 125 over ln 5, or log 125 over log 5, or log base 3.72 of 125 over log base 3.72 of 5. Well, like, what do you mean? Yeah, I'm just showing you, it doesn't matter what base we're using. That's why I put 3.72. You can use any base you want. As long as you have the same base top and bottom, you can simplify any other logarithm. So if you had log base 5 of 7 minus square root of 2. This one's not going to have a nice answer. You have a decimal answer, so what we could do to evaluate it, put it into calculator, log 7 minus square root of 2 divided by log 5. And this will give you the answer. And note, you could use log or ln. And that's one of the reasons why your calculator does not have the log button, because the ln can be used in basically every way. The same. Yes. The thing is, for example, you would have to, if you want a log base 10, you're going to have to change it to, like, if you're graphing, say if you wanted to graph this, not by hand. If you're doing log base 3 of x, you could write this as log x over log 3, and graph that, and you get the same thing. Or you could do ln x over ln 3, and that graph is going to be the same. All three of these graphs are equivalent. So back here, everybody follow how we did that? Are you seeing where these numbers are coming from? So the general rule is log base a of b is the same as log base n of b over log base n of a, where n can be any number we want. And in most of your cases, you're going to use just log. So this is the general rule.